Okay, so now we're going to talk about Chapter 3. So we've gathered our data, we've organized it, now we're going to do some statistics on it. There are two types of statistics, descriptive statistics and inferential statistics. And both of these are statistics in that they come from samples. If we were getting parameters, there is no need to do inferential parameters. We already know the correct answer. So if we were doing parameters, we would be getting descriptive parameters that were also the answer because we have all. But remember, when we're doing a sample, we're making a guess. So descriptive statistics is the answer for the sample, but inferential statistics is the guess about the population. So for example, if I was to sample Northeast State students and find out that 45% of them like the bookstore, that's a statistic because it comes from a sample. It's a descriptive statistic of the sample I took. Then if I wanted to say that, okay, that must mean that of the population of Northeast State students, 45% like the bookstore, I'm taking that descriptive statistic and making it an inferential statistic. I don't know if that's true. I don't know if 45% of students like the bookstore for sure because it's based off a guess. But if I did a good sample, it should be a good guess. So what we're going to do in this chapter is descriptive statistics. Later on, we'll talk about doing inferences with them. So beginning of chapter 2, we talked about things that we were concerned about with data, and the very first one was center. We need to know where the center is so we can tell how the rest of the data varies from it. The most common measure of center is the mean. It's what you're used to calling the average. We don't call it average in statistics because that could indicate any measure of center. So we call it the mean. But you find it the exact way you did before by adding up all your data values and dividing by how many they are. There's formulas here for sample and population. In sample, it's X bar. In population, it's mu. But otherwise, the formulas don't vary. Small n, capital N, but it's still how many data values I have. Because you find the sample or the population mean exactly the same way, in a little while when I show you how to do this on the calculator, it's only going to have the X bar symbol. So it might be mu because you have a population, but it only shows you X bar because X bar and mu are calculated the same way. So take just a minute, hit pause, take your calculator out. And for now, I haven't shown you the way to do it with the features of the calculator. But right now, to get this mean, just add those up, divide by how many there are. So data set 1, add all 6 of those numbers up, divide by 6. Data set 2, add those numbers up, divide by 7. Push play when you want to see the answer. Now, as far as we knew, both these were samples. There was actually nothing to indicate whether it was a sample or a population. So since I don't know, I'm going to pick sample. The first ones, when I put all those in the calculator, added them up, divided by 6, I got 1.54. The second one, when you did it, you get 1.41. If you have any questions on this, email me or ask me in class. Some advantages of the mean. It's pretty reliable. Means of samples drawn from same population don't vary as much as other measures of center, and it takes every data value into account. But sometimes that's the disadvantage. If there's an outlier in there, it can really mess up your mean. Another measure of center is the median. Remember, the symbol for this one is that X tilde, the squiggle on top of the X instead of the straight bar. In a median, you probably have done these in elementary school as well. It's literally the middle number, just like the median in a road is the middle of the road. But to figure out what the middle is, you need to put your numbers in order, low to high, then pick the middle. If you have an even number of data values, after you number low to high, you pick the two middle ones and get the midpoint of those. Remember, midpoint, add them together, divide by 2. So again, take those two data sets and determine the median. When you're ready to see the answer, push play. So if we take the first data set and order it low to high, we see that because we had 6, that the middle fell between 0.73 and 1.10. So we added those together, divided by 2, and the median is 0.915. In the second one, there's an odd set of numbers, so there is an exact middle, so our median is 0.73. Another measure of center is mode. Mode is the data value that occurs with the greatest frequency. Data sets can have one, more than one, or no mode. Mode is the only measure of center that can be used with categorical data. So mean and median we can have with quantitative data. Mode we can have with quantitative data or categorical data. So try to find the mode for these examples. Again, hit pause. When you think you've got it, hit play. Here's what you should have gotten. The first one, 1.10, occurs twice. Everything else occurs once, so that's the mode. In the second one, you have 3 27s and 3 55s, so that's the mode. So there's 2 modes for that one. And in the last 2, there's no modes. The last one example usually gets people. A lot of times they'll put 1, 2, 3, 4, 5 because they occurred more than once, but that's not what mode is. It has to occur more than any of the rest of them. Since each of them occurred twice, nobody occurs most, so it's still no mode. When you were answering this, if you were answering this on a test, you would make sure to write down no mode. Don't put 0, because that indicates that 0 occurred more than any other number. Mid-range is another measure of center. This is probably one of the least used ones, but it is a good one that you can do quickly to figure out a measure of center if you, say, weren't near a computer to do the rest of them. So with mid-range, you take the max and the min and divide by 2. Add them up, divide by 2. So basically you're finding the midpoint of the data. So again, take those 2 data sets, figure out the mid-range. Hit play when you're ready to see the answer. The first one had a mid-range of 2.91. The second one had a mid-range of 2.91. Does that surprise you? It shouldn't, because the only thing that happened in the second data set is it had a 0.66 added. That didn't change the max or the min, so it didn't change where the mid-range is. Advantages to the mid-range is it's very easy to compute, but because it uses that max and min, if there's an outlier, it's going to be pretty far off. Okay, so here's you an example. Take a minute and find all 4 of those things. Find the mean, the median, the mode, and the mid-range. Again, hit play when you're ready to see the answers. So here are the answers for those. And I have forgotten to refer to your notes, but this is on the second page in your notes. If you can see, the mean is very different from the other ones. So is the mid-range. That's because there's an outlier in this data. What do you think the outlier is? If you chose 840, you're correct. It's much bigger than the rest of them, so that was a much fancier air conditioner. If we want to get a better representation of our data, let's get rid of that outlier. So do those calculations again without the outlier. So take the 840 out and figure out the mean, median, mode, and mid-range again. Again, hit play when you're ready to see it. So here's our answers without the outlier. Now see how they're much closer together? So taking that outlier away made our data much more normal so that we could get a better representation of what our actual statistics should be. Now on your paper it says outliers affect blank more than any other measure of center. Well, for our example it was mid-range, but the one you really want there is mean. So you could put both. You could put mid-range and mean. because both those take into account the max and the min. And if those are outliers, it will mess up the data. Okay, now we're going to do a weighted mean. A weighted mean is like your grades in class, okay? And actually in your notes, I have skipped to the next page, but this using the calculator to find mean and median, I'll be coming back to in a couple slides. So you can kind of refer back to this page when you get there. These are the calculator steps in order to do that, and we'll do that in just a few minutes after I talk about weighted mean. So if you want to go ahead and turn the page to weighted mean, you'll be where I am in the slides. This is the formula for weighted mean. Don't worry about this, you're not going to use it. I'm going to show it to you with the formula just to give you some idea of what's going on. And you may have been shown this in the past as far as how to figure out your grades. But there's an easier way to do it on the calculator that I'll be showing you in a few minutes. So the weighted mean, you take the weight, multiply it by the data value, add all those up, then divide by the sum of the weights. So for example, if I was doing class grades, we've got this student who made a 92, 83, 77, 84, and 82 on her tests. Got an 88 on her final, a 95 on her project, and 77 on homework. Tests counted 50%, final counts 25%, project was 10%, homework was 15%. Just a few days ago, first day of class, we talked about this ourselves. In this class, tests are 45%, daily grades 30%, final is 25%. So, and this is very, very common in classrooms for them to have a weighted average like this, that some things count higher on your grade than others. And you're fixing to learn how to figure that out for yourself as to what your current grade is. Students ask me all the time, what's my grade in this class? Well, you don't need to ask me now. You're going to know. It's part of what you're learning in this class. So if I make a little table, test, final, project, homework, I've got my grades down there. The only thing that's a little different is in tests, I've got 83.6. Well, that is the average of those tests. So I took 92, 83, 77, 84, 82, added them up, and divided by 5. Because my weight was for the average of my tests. It's not for each test unless it's written that way. So if in your syllabus it said each of your tests will count 10%, then you would put 10% with each test. Normally, though, they mean the average. Just like in mine, daily grades, it's not each of your daily grades, it's the average. So I'll take all your daily grades, add them up, average them, and then multiply that by 30%. Okay, so if we were going to do this by the formula, the first thing it said to do was to multiply those. Notice I changed the weights from percents to decimals because we can't multiply by a percent, we multiply by a decimal. This is true when we go to put it in the calculator in a minute too. You don't put in percents, you put in decimals. So I multiply each of those, add them up, and I get the sum of the weights times x is 84.5. Then I added up all the weights, all my percents, and got 1 because that was all of them, so it was 100%. Divide the 84.5 by 1, and this person's class average is 84.5. That is what's happening on the calculator here in a minute. You may have been shown how to do that before, but I'm going to show you how to do the same thing on the calculator instead of with the formula. Alright, so on the calculator, you want to put the class midpoints in L1 and the frequencies in L2. And that's true always. Whatever your midpoints are, whatever your data value is, your x, that goes in L1. And whatever your frequency or your weight is, that goes in L2. So in our case, our grades would go in L1 and our percents would go in L2, but you'd put them in as decimals. Once you get them in there, then you want to go back to stat, push your arrow over to the right once and choose 1 bar stats. You want it to look at both lists, so you have to tell it that. So once you push one var stats and press enter, you would put in L1, which remember you do by doing second 1, then a comma. The comma is right above the 7 on your calculator. Then second 2 for L2. So you would get what that line looks like down there, 1 var stats, L1, comma, L2. If you have a newer calculator, an 84, a newer calculator, it brings up like a list and asks you for the different things. Put L1 in the first thing, L2 in the second thing, and then scroll down until it says paste, click paste, and it'll put on your screen 1 var stats, L1, comma, L2. They're doing this to be helpful. I'm not sure it always is, but it's just going to look a little different, but you'll get the same results. There's also a video in my stat lab to help you with this. The link is there. So, and if you get confused, ask me in class and I'll show you. Alright, so if we turn, here again is the things we're putting in. And here are some screenshots of what it would look like. So in L1 I put the grades, in L2 I put the decimals. Then I went back to stats, arrowed over, and chose that 1 var stats. Put in my L1, comma, L2, and then pressed enter, and I get a screen that looks like that. X bar is my mean, so it tells me my average is 84.85. So see, it's much easier to do off the calculator. The only thing on the calculator is you got to remember to put your X values in L1 and your weights in L2. So here's one for you to try. This is the speeds of drivers ticketed by the town of Poughkeepsie police. These drivers were traveling through a 30-mile-per-hour speed zone on Creek Road. How does the mean speed compare to the posted speed limit? So you had speeds, we had a frequency distribution here. We had that there were 25 people going between 42 and 45, 14 going between 46 and 49, 7 going between 50 and 53, 3 going between 54 and 57, and 1 that was going 58 to 61. I can't use those class boundaries, so I need to use a midpoint. So I took each of those, got the midpoint. 42 plus 45 divided by 2 is 43.5, so on and so forth. Just as review, what was the class width? You should have said 4. So if I add 4 each time, I get my other class midpoints. So what I'm going to put in the calculator, in L1 is the class midpoint, and in L2 is the frequency. Okay, so you filled that out down there on the bottom of your page. So above class midpoint, put L1, frequency, put L2. Then on the next page, again, I've got those directions listed for how to do that. If we look back at the problem, the speed limit was supposed to be 30 miles per hour. So how does the mean speed compare to the posted speed limit? Okay? So when you put those in and do 1 var stats L1, comma, L2, you should get a mean of 46.8. So the average speed of cars on that road was 46.8. Well, obviously, this is a road that people like to speed on. The mean speed is almost 16.8 miles per hour more than the posted speed. So this looks like a good spot for a speed trap. Now, again, just with it's a sample. So what things could be wrong? Well, maybe this is a particular day of the week or even a particular hour. If this is around 8 o'clock, people might be more inclined to speed because they're late for work. Whereas if this was Sunday afternoon after church, they may not catch a single speeder. So again, because this is a sample, you need to look at different things like that before you automatically decide that everybody on this road speeds. Or maybe you need to take samples at different times. During the morning, during the week, during the afternoon, during the week, on the weekends. If you constantly are getting things like 46.8, then yes, definitely people are speeding on this road. But if you're only getting it at certain times, then there's probably other reasons like being late to work, or if You know, like this was Volunteer Parkway and it was race weekend. It might be just because people are from out of town and don't really know what the speed limit is. That kind of thing. Okay, so now we're going to get into the second part of Chapter 3, which is distributions, or that variance. We talked about this in Chapter 2, different types of distributions. Symmetric was the normal distribution where it goes low, high, low, and skewed, we had a skewed right, skewed left that usually indicated an outlier. Here's examples of those and how they relate to this mean, median, mode that we've been doing. If you have a perfect bell curve, and I mentioned this the other day I think, if you have a perfect bell curve, your mean, median, and mode are all exactly the same. They're all right there in the middle and it's symmetric. Now it doesn't have to be perfect to be considered normal, and if it's not, they'll be a little off from each other, but they'll still be close. Like remember the air conditioning example, the second time we did it without an outlier, they weren't exactly the same, but they were really close, and that kind of helped you know that this was a normally distributed data. However, if they're skewed, the mean is the one that gets pulled to the outlier the most. So if it's skewed left, your mean would be your lowest number, then your median, then your mode, because that low outlier is pulling the mean to it. If it's skewed to the right, the high outlier is pulling the mean to it, so it would be mode is your lowest number, then median, then mean. Mode is always wherever the highest point in the graph is. Measures of variation tell us about the shape of the distribution, how the rest of the data varies from the mean or the measure of center. The most basic measure of variation is the range. The range is just the maximum value minus the minimum value. Again, because we're using maximum and minimums, it's very sensitive to outliers, so it's not extremely reliable, but it does give us an overall feel for how far our data is distributed. The most common measure of variation is the standard deviation. The standard deviation is how far we are from the mean. Okay? So standard deviation always refers to mean, and it's how far away we are from the mean. It's usually positive, unless all our data is negative. It can increase with outliers, and it's again the same units as the original data values. So if I was doing heights in inches, the standard deviation would be in inches, just like the mean. When you're comparing different samples, you only really want to compare standard deviations when the means are approximately the same. If the means are very different, it's better to use coefficient of variation, which we talk about later. Here's your two formulas for standard deviation. Don't write these down, you're not going to have to worry about them. I've got them up here for one reason only. When I showed you the two formulas for mean, they were exactly the same. But the two formulas for standard deviation aren't quite the same. Look at them a minute and see if you can see what's different. Did you find it? Besides the fact that the symbols are different, because S equals is the sample one, so of course it has X bar and a small n, and sigma is the population one, so it has mu and capital N. S, the sample standard deviation, on the bottom says n minus 1. So there's a little bit of an adjustment to that one because it's a sample. So because these have different formulas, when we do these in the calculator here in a minute, you're going to have an S and a sigma because you're going to have two different numbers. Whereas with the mean, I only have an X bar because mean and mu are calculated exactly the same way. In your notes there, it's got in-class example. We'll talk about these in class next time. So skip on over to the next page to variance. The variance of a set of data is literally the standard deviation squared. We talked about that when you were just starting to learn those symbols. So if you want the sample variance, you do S squared. If you want the population variance, you do sigma squared. That's about all we'll do with variance. Variance is used in statistics because it's a very unbiased estimator, but it's kind of hard to wrap your mind around. Like if you think of standard deviation is 5 inches, then variance is 5 square inches. And if we're talking about the height of a person, that's just weird. What's 25 squared inches in relation to the height of a person? So we're not going to do it very much in this class, just basically name and how you find it. But it is useful in statistics because it's a very unbiased estimator of the population. Alright, so you got an example there on your paper. There's a table that are flight times in hours of NASA's space shuttle. It tells you this is a sample. We're going to figure out the standard deviation, and we're going to use the calculator to do it. So we're going to use that 1-var stats again. You want to put all this data in L1, including the 0. That's a data value, so make sure you put it in there. Then click Stats, arrow to the right, choose 1-var stats. Tell it L1. You don't need to put that L2 in this time because I only have one set of data. So you'll put L1. If you have the newer calculator where it's stacked, put L1 in the first one and have the second one blank. So delete out the L2 if it's still there. Go on down, press Paste, and then press Enter. You'll have 1-var stats, L1, press Enter, and it will give you the statistic. So your screen should look like this. So you put all that in, you did 1-var stats, L1, you should get this screen. So I've got X bar is 217.33, and if you go down you see that S is 105.9 and sigma is 102.3. And so like I was saying, you've got only one mean but 2 standard deviations, because standard deviations are calculated differently, so you have to think about whether it's a sample or a population. In this case, we know we're talking about a sample, so we would use the S equals 105.9. Ignore the little X there beside the S and the sigma. That's just the calculator saying that this is a standard deviation of the X values you gave me. So the X doesn't mean anything, just pay attention to the S and the sigma. So your answer for this one, the standard deviation is 105.9. And on your paper it said, did we use S or sigma and why? You would want to circle S and put because it's a sample. Then it wants to know the variance. So you got to find S squared. To do S squared, you want to enter in that entire S value and then square it. You don't want to enter in 105.9 and square it because you're going to cause round-off error. So you want to enter in the entire 105.920235 and square it. There's 2 different ways of doing that. There's the manual method, which I've shown you down there on the left. You can do ℏ2, which will square it, or you can use the little shortcut squared button. Either way, you get the 11219.1. There is a shortcut method, which I'll show you in class. You push the vars button, which is beside clear. Then you scroll down and choose statistics. Arrow down and choose the S of X. Press enter. It'll pull S of X up on your main screen. Push the square button or do the ℏ2, press enter, and you'll get the same answer. So there is a way to get the calculator to go look at the number it already created, pull it up for you without you having to type it all in, and square it or do whatever else you're wanting to do with it. Okay, the next thing we talk about is range rule of thumb. The range rule of thumb is a principle that for many data sets, the vast majority of samples lie between 2 standard deviations of the mean. So you'll hear this a lot when you're reading different publications. It'll talk about the mean plus or minus 2 standard deviations. It's always plus or minus 2 standard deviations because that's the usual set of data. My minimum usual value is mean minus 2 standard deviations. My maximum usual value is mean plus 2 standard deviations. Anything below that or above that is considered unusual. You'll also run across this some in my stat lab. If you really wanted to roughly estimate the standard deviation, if you're out in the field, not near a computer, and you want to have an idea of what your standard deviation is without doing that long complication, you can do that by taking the range, which remember was the max minus the min, and divide it by 4. This is a very rough estimate, so it's not something we will do in this class, but it might pop up on my stat lab. Okay, this is something you want to know. The empirical rules, so stick memorized beside that. We refer back to this various times throughout the course. The empirical rule, or they've started calling it the 68, 95, 99.7 rule, helps you to know where that usual, unusual falls. I've got a few illustrations for it. So you've got your normal curve, and it's always a normal curve because, like I said, later on I'm going to show you that you can make all data normal. So even if it starts out uniform or skewed right, skewed left, we have a method for making it all go to normal, which is very useful in statistics because I can get better numbers. So this is from a normal curve. If you do the empirical rule with skewed data, it'll be a little off. You can still do it, and we probably will, but it's made for a normal curve. So when you do it with a skewed data curve, it's going to be a little wonky because the data is skewed. 68% is within 1 standard deviation. So when I start there at the mean, which is in red down on the bottom, if I add 1 standard deviation, subtract 1 standard deviation, between those two is 68% of my data. 2 standard deviations, I've gone up to 95% of my data, and that's why that's considered usual. 95% is most of my data, so within 2 standard deviations is most of my data. Then if I go as far as 3 standard deviations, I have 99.7%, so almost all my data is within 3 standard deviations. But notice that's not 100%. So they consider this to go to infinity on both ends, that you can have a little bit of data outside the 3 standard deviations. So the most common is to have 1, 2, or 3 standard deviations, but you could have 4 or 5 standard deviations if you have any extreme outliers. Like that Michael Jordan example, he might be 6 standard deviations above the mean because he's that much different than the actual average. And here's an example of the usual, unusual. So within the 2 standard deviations, within that 95%, we consider that our usual range of value. So any data that falls in there, we would consider it usual. Any data that falls below 2 standard deviations or above 2 standard deviations, we would consider unusual. Alright, so using the previous example, we're going to find the upper and lower boundaries, and then we're going to decide if there's any data values that are usual or unusual. And that's at the bottom of the page you're on. So we've still got that data in the calculator. If you do 1-bar stats, you should still have the numbers up there. That's on the screenshot at the top of the page. In the white are the formulas for usual and unusual. For minimum usual and maximum usual. Minimum usual is the lower boundary, so I take the mean, which was the 217.3, and subtract 2 times the standard deviation, 105.9, and I get 5.5. So 5.5 is 2 standard deviations below my mean. Take the upper boundary and add 2 standard deviations, and I get 429.1. So any flight time between 5.5 hours and 429.1 hours, I would consider usual. So if I look at my different flight times, There's only one that doesn't fall in between those, and that's the 0. So that lowest time of 0 I would consider unusual, and that makes sense. The fact that it was 0 hours means it didn't go anywhere, or it was only in the air for a few minutes. That is very unusual. Okay, turning the page. Here's that other one, that coefficient of variation. Coefficient of variation will be in your homework, but it will not be on your test. So you'll do this in the homework, but don't worry about this as far as a test question. Coefficient of variation is for when you want to compare things that are not alike, okay? And you have two different formulas. Well, you have two formulas down there for sample and population, but honestly, they're exactly the same formula, just with different symbols. In either case, you take the standard deviation, divide it by the mean, and then multiply by 100. So we have this example there on your page to do the coefficient of variation for the heights and weights of 8 players from the Atlanta Braves Major League Baseball team. When you do that, you got to put them in your calculator. So put the heights in L1, do 1 var stats for that, and you'll get a standard deviation of 1.7 and a mean of 73.3. Again, we're using the S, not the sigma, because it's a sample. Take 1.7, divide it by 73.3, multiply by 100. Let me say all that again since I got it wrong. Take the 1.7, divide it by the 73.3, multiply by the 100, and you'll end up with 2.3%. Now do the whole thing all over again for the weights. You could put them in L1, or you could just put them in L2 since you've already got something in L1. Then when you do 1 var stats, you would just do L2 instead of L1, because that's where they are. You would get a standard deviation of 21.5, a mean of 195.6. Put it in the formula calculator, you get 10.99%. So you can see that there's less variation in heights than in weights. They only vary 2.3% from each other in heights, but they vary 10.99% in weights. Does this matter? Depends on if you're the coach of the baseball team. I asked about this in class one time and got somebody who actually knew something about it. And they said that you do tend to like your baseball players to be more uniform because it helps with batting and pitching. So it is actually more desired in baseball for the baseball players to be pretty uniform to each other, to be around the same height, around the same weight. If you have a lot of variation in weight, usually your heavier players are your harder hitters. So they're the ones more likely to get a home run. But it makes it different as far as pitching, if you have different weights and different heights. So it is actually desirable for heights and weights to be about the same. So if this was my team, I wouldn't be worried about heights, that's pretty fine, but weights, I need to get them more uniform in weight. Okay, so other measures of relative standing. The last part of this is we're just going to kind of talk about some other measures and then do one more type of graph down here. There's different ways that we look at our data values in relation to each other. Some of this stuff we're going to do at different times. This is mostly definition things for you to know when they talk about it. The most important concept we're going to talk about is z-scores, but we're not going to do much with them now. We're going to do a lot with them in Chapter 6. So right now I'm just running through some definitions. That z-score, like I said, is going to be very important later on. All a z-score is quite literally how many standard deviations you are above or below the mean. So I'm going to spread this out just to look at the graph. So here is my empirical rule where I'm adding standard deviations, subtracting them. At the mean in the middle, your z-score is 0. So this line down here are your z's. And this line up here is your x values. So down there, when I'm at the mean, I have a z of 0. When I add one standard deviation, I'm one standard deviation above the mean, so I have a z of 1. So if you're going to the right here, your z will be positive. If I go to the left, my z's are negative because I'm below. So they're positive up here because I'm above the mean, negative down here because I'm below the mean. So a z of -2 indicates that I am 2 standard deviations below the mean. So z-scores are literally how many standard deviations you are above or below the mean. Percentiles, you should be kind of familiar with, because most of you had to take an ACT to come to college. And in your ACT or SATs, they always tell you what percentile you are. Percentiles are how you compare to everyone else who took it, so it's where you rank in that 100%. It starts down here at 1% and goes up to 100. And the way this book indicates them is with these P's and a number. So if I was this P99, I'm here at the 99th percentile. So it means that 99% of people did worse than me and 1% did better than me if I was talking about a test score. Okay? So then if I was, let me erase that. If it gave me something more like a P of 50, that means I'm right here in the middle. So I'm at my mean. Pretend that's a straight line. And half the people did worse than I did. And half the people did better than I did. Okay? So percentiles is literally, I take that curve and break it up into each percentiles 0 to 100. And whatever the number is where I'm falling. Quartiles are similar to percentiles, except I'm going by 25%, thus quarter, and the little numbers beside it indicates which quartile. Again, I'm going to blow the graph up and talk about it. So down here at the very bottom, this very lowest number is your minimum. This very upper number is your maximum. And then it's broken up into the 25s in between. So between my minimum and my first quartile, there's 25%. Between the first quartile and the second quartile is the same thing as the median, is 25%. Between the median and the third quartile is 25%. And between the third quartile and the maximum is 25%. So I'm taking my data and breaking it up into quarters. This last one, those quartiles, are called the 5-number summary. See, there's your minimum, Q1, median, Q3, maximum. And actually, these are in that 1-var stats. I can use this idea of quartiles to figure out if something is actually an outlier. So all the time up till now, we've looked at things and said, yeah, that's probably an outlier. But now is the first time you got a formula for actually determining if it's an outlier. So to get an outlier, you first have to figure out the inner quartile range, the IQR. You do that by taking Q3 and subtracting Q1. Then use that number to get a lower fence and an upper fence. I have no idea why they call it fences in this thing. I guess maybe to make it different than the usual and unusual boundaries. But to get the lower fence, you do Q1 minus 1.5 times your IQR. To get the upper fence, you do Q3 plus 1.5 times your IQR. If it's lower than the lower fence or higher than the upper fence, it is an outlier. And outliers we've talked about several times. We can use this 5-number summary to make a box plot or a box and whiskers graph. The middle part, the Q1, median, and Q3 make the box, and the last 25% between the max in Q3 and the min in Q1 are the whiskers. This is a good example of a normal distribution in a box plot. The whiskers are pretty uniform around the box, so that's making a nice normal distribution. If you think of it in a normal curve, it's just coming up and coming down. Whereas this one, most of my data is here, and then it spreads way out that way. So see, that one's more of a skewed right distribution. So some football coach makes a whole lot more than the rest of the football coaches and is skewing the data. Sometimes when you have those outliers, what they'll do in a box plot is instead of having that big long whisker, they'll just represent the outliers as dots. So you've got this nice normal distribution here, and then you've got these two outliers out here. So it's showing you that the original data had outliers, but that if you take those away, you've got a decent normal distribution. This was that pulse rate of females that we did originally, so they took the top two and made them as outliers. Okay. Now, there we go. So, if you turn on your last page of your notes, you have this example here. These are the test scores of, pardon me. Didn't mean to be drawing on it, I was trying to scrunch it. Okay. These are the test scores of 15 employees enrolled in a CPR training course. We're going to get a 5-number summary and construct a box and whisker plot for the data. Find the IQR and see if we have any outliers. I thought it was ignored. Okay, so you want to put that data in L1, do 1-bar stats of L1, and then if you scroll down, you will see your 5-number summary at the bottom of 1-bar stats. So your 5-number summary should be 5, 10, 15, 18, and 37. Now, if we take that, oops, I skipped some pages. We can do our lower and upper fence to determine if this is an outlier or not, or if we have any outliers. So to get the IQR, take Q3 minus Q1, so that would be 18 minus 10, or 8. Then to get your lower fence, take Q1, which is 10, subtract 1.5 times 8, and you get negative 2. So your lower fence is negative 2. To get your upper fence, take Q3 plus 1.5 times the IQR. So 18 plus 1.5 times 8, you get 30. So that's your upper fence. So now, if you look at that original data, there's no negative numbers, so there's no low outlier. If you look at your original data, there's one number, the 37, that's above 30. So 37 is an outlier. Then you can take this and make a box plot out of it. I do not have a box plot in my PowerPoint, so we'll do that next time in class and remind you how to do it on a calculator. If you look back at the calculator instructions in my stat lab, it shows you how to get a box plot on your calculator from this data. So we'll do that in class next time. Let me know if you have any questions, and we'll discuss all this more in class.